So let's look at a few examples of how we relate these quantities to each other. First of all, I want to start with chapter 10. We're going to do number 50. And this asks the question, what is the angular speed of the planet Earth and what is the linear speed at a latitude of 30 degrees? So our strategy here is going to be looking at the relationship between theta, omega, and position and velocity. So we're going to look at how these things are related to each other. And for my picture here, I'm going to go ahead and draw my Earth. So here's my planet Earth. And I've got a point on the surface, which we've decided is 30 degrees latitude. And I know that the radius of the Earth is given in your book as the radius of the Earth. There's a symbol for the Earth is equal to 6309 kilometers. And the thing we don't know is at this point, which is rotating around the Earth at that latitude, what is the angular speed and what is the tangential velocity along that circle. So if we were to look down on the North Pole, here's our circle at 30 degrees. This would be the circle at the equator. And the question is, what is the speed of this person who happens to be going around at that latitude? This is the North Pole right here. Okay, so we have our knowns, we have our unknowns, and so let's go ahead and figure this out. So first of all, let's look at the angular speed. So the angular speed, this is our solution here, solution. So the angular speed, so we calculate the angular speed by looking at how long it takes for this orb to rotate. So one full rotation is going to be 360 degrees or 2 pi radians. And we'll do this in radians because the units of angular rotation are radians per second. So our angular rotation is going to be equal to 2 pi divided by how long it takes to go around in one complete circle, and that's roughly 24 hours. And we want this in seconds. So we're going to multiply this by 60 minutes in an hour and 60 seconds in a minute. So that's going to give me something in seconds. And that's equal to 2 pi divided by, if I multiply that all together, I get 86,400 seconds. And if I go ahead and calculate all that, according to my calculator, I get 7 times 10 to the minus 5 radians per second, which is not, this number doesn't necessarily intuitively make a lot of sense to me, but we're going to hang on for a second and evaluate that in just a second. So the question then becomes, well, how fast am I moving on this globe as I go around? Well, if I'm looking at my point right here and I'm asking how fast it's moving, it's going around in a circle here at 30 degrees latitude. So that's not a circle at the radius of the Earth, it's a circle of the radius of this circle at 30 degrees latitude. So let's look at this triangle here. If we imagine here's the North Pole right here, here's us at 30 degrees latitude, right? This is the equator down here. And so this radius of the circle that we're actually rotating around is that right here, right there. And that's going to be, we'll call that r, and that's r is equal to the radius of the Earth times the cosine of 30 degrees. Okay. And then we have our expression for the tangential velocity. That's just going to be equal to that radius times my angular velocity. So that's equal to r Earth cosine 30 times my omega right there. And if I work that out, keeping this in kilometers, the units would come out in kilometers per second, and I get 0.38 kilometers per second, which is the same as 380 meters per second. Now, if I Google, say, equatorial speed of the Earth, I get something like 460 meters per second, so this makes sense. But let's see if we figure out what's going on here. If I take this to 0 degrees latitude, then that's going to be at a maximum. It turns out to be about 460. If I take that to 90 degrees latitude, cosine of 90 is 0, and I get a tangential velocity of 0. In fact, if you're standing exactly on the North Pole, you shouldn't be rotating at all, right? So we call that, so for our significance, we see that the function behaves in the limit, and then when we checked our answer, we wound up getting something that seemed reasonable for that.